But any kind of historical inaccuracy, please let me know. I really would like to know. Okay, so that now after that, this is of course this got Sergey and Kobe, and I think I'm a great admirer of both of you. And I think the first time I really met you for a little bit longer time was in Toronto in 2009. I think I met you before that, but really the first time I met you was in Toronto. And I very much admire you. I admire your leadership. I think I'm sure we said this before, but how you led the group also back then, and particularly where you always lead us to was, does it work? Would have been better if it worked. I have to turn it on. Here you go. Does it work now? Yes. So where you always lead us to was, of course, the various pubs in Toronto. In particular, Sergey was always organized what he called the Midwest Model Theory meeting, which was in the pub next door to the Fields Institute. So if you haven't been at the Fields Institute, this used to be the pub or the bar right on the other side of the street. And we'll go there often. And I was very, very happy that in particular Sergey organized this so often, because we really had the chance to meet when I was just I just finished my PhD. It was really always a great opportunity to talk, and it was particularly nice to talk to Sergey and Kobe back then. It's unfortunately it's closed, so it didn't survive the pandemic. So when we had these two meetings back this year, it was closed. I mean, I'm showing this picture. I think it's appropriately tilted for a pub, but it was not necessarily a nice one. That's the closest one. It's a shame that does. Okay, so I want to, as I said, I want to talk a little bit. No, it works about something that goes back to Kobe and Sergey's joint work. I think this will be a little bit about this. I think the second joint paper. So a classical theme in model theory, and dating back to Boris's trichotomy conjecture, is, does model theoretically tame structure that exhibit well-defined linear behavior? So there's some really striking nonlinear behavior in the structure, actually define fields. This was in some sense Boris's trichotomy conjecture. And then Peterzil and Starchenko, they proved this in the case of O-minimal structure. So in this time, they proved that really it's a trichotomy conjecture. I will more be interested in this case where they show that if you have nonlinearity, then you actually define a field. So I hope you can read this here. This is the first page of the paper they wrote back then. It's called the trichotomy theorem for O-minimal structures. And of course, many of you know this theorem better than me, but maybe some of you have never seen it before, than the youngest in the audience. But it roughly says that if you're in an O-minimal structure, I should probably just read it because they say it so nicely. So you take an O-minimal structure. Classical examples are ordered divisible by being proven, real closed field. We prove a trichotomy theorem for the structure that an arbitrary O-minimal M can induce a neighborhood of any A and M. Roughly said one of the following. So either it's the point is either trivial, or there's on this neighborhood there's an ordered vector space structure, or there's a real closed field on this. So they're really in the O-minimal setting, you had this really nice trichotomy. Somehow the positive answer to Boris's trichotomy. Again, I said that this is really prior to my time, so I want to show you here actually Dougal's, probably to the leads, Dougal's review, if I may, in the JSL. And I want to read I don't want to read everything because I have a couple of slides, and I just want to point out maybe what I really want to state it. So what I'm really interested in is really in the part, and this is the line down here. One form of the conjecture was, from Boris's conjecture, was that a non-locally modular strongly minimal set interprets an algebraically closed field. Of course, as we all know, this was refuted by Hrushovski before. Actually, it's kind of interesting. I want to say this is amazing. I looked this up the other day, and I wanted to have the review for this paper from the JSL, and I looked at what other papers were in the same were reviewed in the same JSL issue, and it's really striking. I think below this paper is a review of Alex's proof of Rx, and above all that is Zilber Hrushovski's it's a risky geometry paper, and in the same issue, it's also the review of precisely this this theorem of Hrushovski's. So it's really, I mean, it's first of all, it's great company to keep, and it's a really amazing time for model theory back then. So what I want to come back to Kobe's result here, and so what they of course did, they proved this in the case of O-minimality. Here is a nice, Dugald makes a very nice paragraph of explaining what O-minimality is, what I hope by now you all know. One thing I do want to point out, and this will be more important for what we're gonna talk about in a little bit. So what I want to talk about, what I actually did with Erik, is what Dugald points out here is that what does O-minimality and strongly minimality have? They have definitely a good dimension theory. You can see this probably pointed here. Yes. Good dimension theory, like model rank, like Morley rank, topological connectedness playing the role of Morley degree, and some structure theory for definable groups. Okay. Of course, in the setup from Kobe and Sergey, an important role, and of course Boris's conjecture too, was that the both structures were geometric, so that the algebraic closure was an excellent exchange point. It was in pre-geometry. And of course, what they needed in both cases, of course, and it's what essentially strongly minimality and O-minimality comes in, is that any definable family of subset, there's a finite bound on the number of the size of the finite members. We'll talk about this a little bit more. But of course, that's why you can prove the trichotomy conjecture in for O-minimal structures. You had a little bit more. I mean, there has to be something that works in the O-minimal setting, and Dugald writes here. O-minimal structures come with a topology with respect to which definable function have good continuity properties and differentiability properties. And this is also maybe important to the development of O-minimality in general. Reclosed fields have many natural O-minimal proper expansions. And of course, as I said, best one known is Alex's proof of the O-minimality of Rx, which is, as I said, the review just below. And right, so here's a little bit of prehistory that Dugald describes here. So that this comes out, this is the culmination of a program of Peterzil and others to prove this Zilber dichotomy in setting. And it's a really important, as you know, I know, paper with deep application. It comes up again and again, even, what is it, 25 years later. One last thing I do want to point out here, I think this is interesting that this is written here. So these papers, of course, have different flavor from recent literature and O-minimality. I mean, recent means in 1990s, in that it was really more about, let's say, the model theory of O-minimality. And this is somehow a little bit what Chris talked about, in contrast to, let's say, the really great results of that time on O-minimal analytic expansions of the reals. So maybe that's a good point to mention. So Chris made this kind of claim that when he talked to fields with many people, and I meet, of course, younger people, that they didn't know about all these results from the 90s. Now, of course, I am one of these people he probably talked and mentioned. And it's really true that kind of when you came into O-minimality, let's say 10 years after all of this, what you would read is Lau's excellent book, right? And you would learn about cell decomposition and so on. And you would read all these papers, how you construct O-minimal structures, and Lau's non-existent second book. And but what there never was, and this is, I think, one of the reasons why some younger people, me included, didn't know all the kind of results from that time, is because there's just no book on the model theory of O-minimality. So I think we're really missing all the others. You always have to be careful when you say something like this, because if you say, then you have to write the book, but I don't want to write that book. Okay, so this was Dugald's review, and I will come back to some of the things that Dugald said throughout. So now I want to connect this to some stuff I did with Erik. And so maybe the first result I want to mention is, I mean, it's a more kind of, if in particular, if you never have seen the kind of the Peterzil-Starchenko trichotomy, then maybe you want to take some of the earlier results, which are a little bit more hands-on, if you don't want to think about algebraic geometry, about pre-geometry. So one of the first results was that if you take a subset of R to the n that is semi-algebraic, but not semi, it's a semi-linear, so definable in the real field, but not in any vector space over the reals. Then actually this structure defines restriction of multiplication. So if you have anything semi-algebraic that is not semi-linear, then you define already multiplication locally on interval. I want to give you, so what this in particular means that on the unit interval, you can define a field structure. So I want to give this a name. So let's call an expansion of the, well, whether you even really need order, the real line field type, if there is a definable field, but with some further properties. First of all, that the domain of the field is an interval in the line, and that the field, together with the order that is given on this interval, so this is the usual order on the reals, is isomorphic to the real closed field. So it's much stronger than just interpreting a field or just defining some fields. Really want to have a field on some interval that is isomorphic to the real field. And so what in the paper, in the MPP paper, what they really reduced down to, and this I think the most of the work that was really probably new, is that they reduced down to the case that you have a continuous C2 function that is non-affine, and then they show that the resulting structure, where they just have this kind of function, that this is of field type. In theory, I think they really state this as if F is semi-algebraic, but the proof really works out in full generality. You really just need C2. And this goes back to some of the argument is that I could have done it in detail, but I didn't have the time. Goes back to an argument of Marbinovich and Zilber, where they really have to talk about, I mean, you have to talk about tangents and how they compose and so on. Okay, so what you need, and now I'll come back to, in order to somehow get this kind of behavior that I was looking for. Remember that the kind of what I mentioned at the beginning was that really what we want to talk a little bit about is that if you have well-defined nonlinear behavior in the structure, then you actually find a field. And so here's a theorem. There's a typo in there, and you can see whether you find it. Is from the same paper that Chris mentioned yesterday. So it's from Hrushovski and Steiner in 95. What they prove in there, okay, as I stated, this is actually not that hard. They prove that if you take the, so strike this out, otherwise it's easy. They let that R be an expansion. So this should have been dots and not a multiplication. So take an expansion of the real additive group, take an expansion of a real additive group, take a function f that is definable from R to R. You can do this also in higher dimensions. Then you can always find for every n, the function c is f is cn outside a finite set. If you do this over the kind of over the field, then of course that's reasonably easy because you can actually define the derivative. But here they really had to do some extra work, and so they used the result of Boras and Widder to make this work in cell decomposition in a non-trivial way to prove this generic continuity for homonymous structures even over the additive group. And then if you put this all together, then really, sorry, you get what you want. So you get, if you take an homonomial expansion of an HOMA, then it's either field type or it's a reduct of the ordered vector space. Because if you take, well, you take anything, you can just check, do you have a C2 non-affine function? Then it is of field type. Or if it's, but you know, so if you have any function and it's not affine, then you can use this theorem to make sure it's C2 on an interval, and then it has to be field type. So that means that every function, if you don't have a C2 non-affine, everything has to be affine. And so you can show then that, I think they make this argument in the paper, that then R is either of field type or is a reduct of the ordered vector space, where the ordered vector space is really just, you take the relative group and it all scalar multiplication. Okay, so you here in this setting, you really have what you wanted to have. You have the non-linearity implies field time. Okay, so this is from, as I said, from the late 90s or from mid-90s, and now I want to kind of talk about generalizations of this. So really, what I now want to talk about the working on the reals and drop or change this assumption here. So I want to talk, okay, how important for all of this is, or let's say, how important for this behavior is the omnimality. Okay, and so now for that, I will introduce somehow the following tameness notion. As you can see, slightly in the back, this will be the idea of having somewhat the weakest possible generalization of omnimality, and I will tell you why this is, or why I argue that this is the weakest one. But let me first state what it is, and I will give you the equivalent definition, which is maybe easier to at least remember. So the take and suppose you work in some expansion of the real additive group, and suppose you have a set that is definable, or have a definable order. That's really what this is. You have X is some subset of the line. You have this is a linear order, and we call this a dense omega order. Well, if it's the underlying universe of the order is dense in some interval, and if it's order isomorphic to the natural. So it's in some sense definably countable. And so the kind of claim I want to make, I'll give you an explanation why and try to put this in a larger framework in a second, is that the idea here is that if we want to have that non-definability of dense omega orders is the weakest sensible generalization of omnimality.
These are just an expansion of the reals.
Yes. So I mean, so the main point is that this being a dense omega order, why I have this here, depends on some definability. So it depends on this ambient structure. So it's kind of, it doesn't live on its own. The real reason where this comes from, this might look a bit arbitrary, is that if you take an expansion of the real field, and you define such a dense omega order, then you define the integers, and vice versa. The other direction is kind of easy. But so what it says is that if you define one of these dense omega order, then you define the integers. If you define the integers here, you're essentially working with second order arithmetic. So you can define, as always, all Borel sets, or projective sets, and so on. So from a model theoretic point of view, whenever you have a dense omega order in this kind of structure, you're really working in descriptive set theory. Okay, so this kind of says that if you have a dense omega order, then you're somehow wild, and you can, even without the multiplication, you can say something, but I don't want to, I will say this later. But so even if you say, okay, good, then you don't define a dense omega order, but does that mean anything? So there wouldn't be not a very good tameness condition if it doesn't imply any kind of tameness. And the tameness it implies is the following. It's essentially a strong bare category theorem. In order to state its bare category theorem, I have to say what F sigmas are. And I don't want to use the usual notion of F sigma. I want to use B sigmas. This is definition going back to Miller and Spizek in their paper for the field, and then Dolic, Miller, and Steinhorn in the setting of a group. So they say that let R be an expansion, again here, of the, let's say, of the additive group, but it doesn't really matter. We say that X is the sigma if it's an increasing union in some sense of compact sets. So you have a definable family, definable in R, the definable means such that X is a union of this family. And this is increasing, yes, it is increasing in R and decreasing in S. I should have said this, the positive reals. So it's if you would work over the field, then you can just take you can forget about the S, because you have a pole and you can make something small big, and then this kind of increasing thing is really the same as just ranging over one parameter. So in some sense, this is a kind of generalization of F sigma sets, because there would be somehow countable union of a compact set you can make. But so you replace this countability requirement by this kind of definable increasing union. And so what you get then, and this is that if you have an expansion that does not define a dense omega order, okay, so this kind of weird tameness condition I put at the top of the slide, then something good has to be true. And the thing that has to be true is a strong version of their category theorem. I always think of this as a kind of the dream of a descriptive set theorist, because then they could do geometry. So that what it says that every the sigma set either has interior, and so now that the usual category theorem would give you that and this would be F sigma would give you interior or meager, so the union of countable union of nowhere dense sets. But meager in the descriptive set that doesn't give you anything of what we would recognize as a geometric property. So really what we replace here is meager, which could be dense and codense, by nowhere dense, so by really small in our sense. So that's why this is much stronger. And that's with this kind of stronger category theorem, you can do descriptive set theory, but in a geometric way, because you have smallness and not just meager. If you want to compare this to omnimality here, really what you should read this of is that if you in omnimality, if you have an increasing definable union of finite sets. So if you have something like this, where these things are finite, then in omnimality, because you have uniform finiteness, the union has to be finite. It goes bigger, 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 and so but it has to stop because you have uniform finiteness. And you can think of the strong bare category theorem as a version of uniform finiteness in this sense, because you have an increasing family of no finite sets. This has no chance of being finite in general, but it will be nowhere dense. So it stays small in a clear described way. And this is where this comes. So if you don't like this kind of definition up here, this is equivalent. Just think of this as all the expansions that satisfy the strong bare category theorem was satisfying this kind of version of uniform finiteness. Okay, so good. So now let's come back to what we really wanted to do. We wanted to talk about nonlinear implies field type, implies of having a real field around. So I give this a name, and Erik gave this name, so let's call this type A, and we'll see what's type A in a second. If you do not define a dense omega order, so if you satisfy strong bare category theorem, and then indeed we can make Hrushovski and Steinhorn's theorem work in that setting. So this is the generic differentiability for omnimality in this way larger setting. So suppose R is type A. Fix some k, that will be the kind of differentiability here, and then let U be an open set. And so now take F to be, and we can take the continuous function if you like, or that the graph is the sigma, that's slightly weaker condition. If you want to think about the sigma, think of this function here as continuous. Then there is an open dense subset of U, such that on that set, F is CK. So you have this open set. You can throw away this nowhere dense thing, so this small thing, and outside of it, this will be CK. In particular, if you do this in the line, then you have an interval. I mean, you already know where then set. So you have all these intervals on which F is CK. And so this is really now we apply this. The result that we had before, and you get this kind of dichotomy in this set. So now if you have a type A structure, either every continuous function is locally affine outside the definable nowhere dense set, or it's field type. So how do we get this? Really, I mean, if you take this R to R, then you have a function. You know that it's by this theorem, it has to be locally CK. If it's not locally affine, then by the result of Marker, Pillay, and Peterzil, you get that this then has field type. So from and you're done. So together with these kind of adjustments of this traditional results from the 90s, you almost immediately get this kind of non-linear behavior, linear versus field type behavior in this vast generality.
Result that you were forming before that F does not get semi-algebraic. You watched this before. Yes, the last result of Pillay.
So I can show you. Sorry. Yes. So
Oh, yeah.
So they prove it in the case that it's semi-algebraic. That is not important. I think this was actually known at the time that this was not. So I mean, we give this proof again in a slightly more generality, but I do think this was. I mean, I couldn't find an explicit statement in any paper. I found statements like this that cited this result in other papers like this, but in that no original source for that. So I believe that this was at least then in the proof of this result, but it's. Okay, so sorry, yeah, thank you. So then, even here, so then in Sergey and Kobe's work in the late 90s, they proved also, so that one of the results they proved in there, and I think this is a little bit better to state. I call this Peterzil's omnimal analog of, but I'm not sure whether this is the right. But I think in one of the earlier papers of Kobe, he makes this kind of conjecture or some kind of this in this direction. That take an omnimal expansion of the real additive group, then the following are equivalent. So field type is what we're looking for, and here is this kind of connection to curves. I mean, so take a definable family. I mean, maybe you can even make it just say it's a curve. Take the family of curves. That's really what this means here, such that the family is two-dimensional. So what is meant by that is that each, okay, that's mean that it's a curve, but that each of these different curves, they only intersect zero-dimensional here means finite, in finitely many points. So if you have this two-dimensional family of curves, then you actually have a field. So this was, I think this was some of Boris's, if I have my history, this was kind of Boris's conjecture in the case of strong and minimal, but the Peterzil and Starchenko proved this here in the case of omnimal. And indeed, this is a really strong notion of kind of having non-linear behavior and getting a field. And indeed, again, here's the same case. So if you move from orthogonal to type A, you get the same result. So if you take an expansion of the real additive group, no, just type A, then you can your field. If you have a family, you have to put here d sigma. But if you really want to say curves, say curve, then it really doesn't have any different statement here. Such that if it's two-dimensional, then you have field type. So again, you have this kind of really strong non-linearity implies field type.
Philipp?
And right, so I don't want to the proofs, but really I want to some of paraphrasing Dugald here that what goes into this is really what goes into it in the omnimal case. You have in the type A case, you have a good theory of dimension, you have definable selection. We proved the Hrushovski-Stein of generic smoothness, and we have this strong dicategory theorem as a replacement of uniform finiteness. For these sigma sets. Okay, so not for all definable sets, but for these sigma sets. Before coming back to talking a little bit more about, actually, how much time do I have? How much? Okay, yeah, good. Before coming back to this kind of nonlinear implies field type questions, I briefly wanted to take the opportunity to talk a little bit here about this d sigma. So you might say, okay, d sigma is kind of what this is about. It's a small set part of all the definable sets, or is this, I mean, all these kind of results for omnimal structures, so for all definable sets. So is Philipp really cheating here in that when he's talking about d sigma sets? So that I briefly want to introduce that the notion of an open core. So the open core is really that if you take any expansion of any topological structure for that matter, but let's say be an expansion of the real additive group, then the open core is really the reduct generated by all open sets. I mean, you do this in any way, you have a definable topology, you could do that. And you can show that the d sigma sets, okay, obviously all open sets are in this core, or closed sets are in this core, and you can also then show that all d sigma sets are in this core. So you somehow can think of this open core in some sense as a Borel hierarchy of the structure, or the projective hierarchy of the structure. So everything that is generated by these open sets. And so the Chris Miller's conjecture is that the strong Baire category, more or less, that the strong Baire category theorem not only holds for all the sigma sets, but really for everything in the open core. And if you would have that, if you would have that, then this would really go through all these kind of arguments would go through for everything in the open core. And it would also show that really, if you take a definable set, or take a definable set in the structure, then this would be some set. And you take the closure, that's a closed set that would lie in the open core. So everything would be in every expansion of type A, really every definable set would be dense and codense in something that is well behaved in this sense. So really you would get everything you can possibly hope in this generality. Okay, but I want to come back to this non-linearity implies field. So the question, so I generalize this to this rather large class of structures here, type A, and we'll say a little bit about what they actually are in a moment. But you could ask, so we started with ominomality. Does every expansion of the real additive group that exhibit kind of well-defined non-linearity actually find a field? So how crucial is the kind of model theoretic tameness in there? Is it really about model theory? Is it about definability? What is it about? And I want to show you here a little bit what we know in this direction. We know quite a bit actually. So what Erik suggested was that, I mean, so you he come up with this notion of type A, but he came up this in also of type A, B, and C. So what are those? So type A is that you do not define a dense omega order. Type B is you define the dense omega order, but not every compact set. And type C is you define every compact set. A priori, this looks like nothing really kind of special because it's it's obviously trichotomy, or almost the opposite of trichotomy. But this so far this has no meaning. It's just this kind of logical. There's just logic in there. Nothing. I mean, just basic Boolean calculus. But one of these kind of observations I want to make here is that. So we know that in type A structures, we have that non-linearity implies. In type C structure, that's trivial because I mean, they're always every compact set. So you have every Okay. Okay, sorry, I'm standing too far. I can stand here and then. Yeah, it's no. Thank you. So type C expansions are always field type because I mean every field is essentially multiplication, and the graphs of addition and multiplication are in any bounded interval are compact. Bounded closed interval are compact. So they are truly definable. Note that this that's also one of these order results that this doesn't necessarily mean that full multiplication is definable, but on every intervals they'll get it. So really, if you want to does non-linearity imply field type, then you have to do it just for type B expansions. We already know a little bit about that. Is that if you by one of my earlier results, a type B structure cannot possibly be of field type. So if you type B structure, so if you have dense omega order and you have field structure around, then you always will be type C. So if you have type B is really kind of very, very narrow thing, because if you add too much to this dense omega order, you always get type C. So really what is left to do is really to study type B structures. Right, but before I do so, I want to give you here really just the picture you should have in mind. And it's kind of a nice picture. Again, this was Erik's idea. It's kind of nice, what we call the tetrachotomy. This kind of nice behavior that you see for all expansion of the real additive group. So this now for all expansions of the real additive group. No tame restriction. So two things can happen. Either, and this is linear versus linear here on the left-hand side, and this is dense omega order or no dense omega order. So tame, in some sense, tame or non-tame. In the case of if you have a field type and you have then you have this type A, field type B, fine down here, and you have these two other types here. So type C, Let me give you here an example, just to give you some, like Gabe does so nicely in this model theoretic universe that he has. So an standard example of a structure that is type C, and field type is, of course, where you add the integers to the real field. Then all these kind of model theoretic, or I should have changed this here, all these kind of nice model theoretic structures will lie in this part here. For example, omnimality will be a small part. Down here, up here, the real field, here the additive group. Local omnimality is right here. For example, if you take the reals without multiplication and you add these integers, and you get local omnimality here. D-minimality here allows example from the early mid-80s, where you add the 2 to the z. You can do this if you wanted to keep it affine. You just forget about multiplication. And then there's also kind of the biggest thing I wouldn't want to talk too much about. This is noiselessness and so on. This is essentially saying that the bare category theorem holds for this, or the strong bare category theorem. So we have examples of Cantor sets for which this is true. Okay, so this is kind of the overall picture. And really, what from the linearity point of view, the only thing that the linearity versus versus field type, the only thing we don't fully understand is type B. So I want to take the last few minutes to talk about how this looks like in this type B structures. Okay, but hopefully I'm happy. So I just want to give you a couple of examples of this type B structures, because they're somehow, from a model theoretic point of view, not so much studied, because they do not satisfy nice model theoretic properties. So they kind of, if you take it, for example, take a subfield of the reals that is quadratic, so and take the vector space generated by that field and add a predicate for z. That is type B. But you can easily see that okay, I will not show that it is type B. I will not show define it in some order. But what you can see nicely and directly is that the bare category theorem fails. Okay, so take one of these kind of quadratic numbers and consider this family here. So this is really just multiply a natural number by m by r, and take the floor. So you always be between 0 and 1. And you make this a family by restricting it with a natural number. So as n runs to infinity, this set will be larger and larger, but each of them is finite. And now if you take the union of that, so this is a union of an increasing family of closed sets, compact sets, then what you will get is this set here, this Rn minus n. This is, I mean, you don't even need to see this. This might be something one to know. It's dense and codense in 0, 1. So this is essentially Diophantine approximation of the real number R, and this fills up the interval 0, 1. But this is DC. And so these kind of, so this is a kind of an immediate counterexample to the bare category theorem, because it's obviously d sigma, but yet it is not either has interior or is nowhere dense, because it neither has interior nor is nowhere dense, because it's somewhere dense. And okay, and another example, a more geometric example, I don't give you the, is the you take the ternary Cantor set, usually middle third Cantor set, where you keep on throwing intervals and in the middle third intervals, then and you put this on the real additive group. This is also type B. And to because I said I just want to produce a counterexample to the d sigma. This is a structure. So you have the reals with this multiplication by r and the predicate for the integers. Why is that uniformly definable? Because the floor function is uniformly definable. Yeah, because we have the integers. So you do, yes, of course. I mean, otherwise, if you forget about this here, then you're minimal. You're good, yes. And then this is what you get. So this kind of, you can see this approximation. In this case, this structure actually is. Okay, I don't want to go into that. This structure actually has a decidable theory, and this depends crucially on K being quadratic. If it's not quadratic, it doesn't. And thank you for the question. So what we still want to do is to know that does every type B structure that is not of field type So we know that all of them are not of field type, but do they actually have are they actually linear in some sense, suitable sense? To give you an example of what kind of functions are definable, because we talk all about function, not so much about pre-geometries. This is a function definable, the graph of a function definable in here. And what it does, it simply take any point in 0, 1 and map it to the distance to the ternary Cantor set. So the 0 points of zeros are precisely the Cantor set. And the farther you go away from the Cantor set, the higher goes the function. For example, here at 1/2, not surprisingly. So the function that we see in type B structures are really kind of locally affine functions, outside the nowhere dense set. And what you can also see, okay, I will show you here the result. So if you now want to say, okay, if you want to have this general non-linearity implies field type, then you have to have that. If you do not field type, you have to have some clear linear behavior. So the minimum we get from these old results is, of course, that every C2 function has to be affine, because if it wouldn't be affine, then you would have to be field type, but we know it's not field type. So then what would how much better can you get? And there we only have really partial results. One partial result here is that, but that's, we can join with Erik, is that if you have a definable family of linear functions, then this has only finitely many distinct elements. So if you have a function like this here, and you see that the slopes here are either 1 or -1. Okay, and so that means that if you cannot have a function really where locally you would have infinitely many different slopes. So the restriction is rather strong. But really what you would like to have, and I will just have this conjecture on the next slide, what you really would like to have is that in this type B structures, and we really don't know the answer, is that all functions look like that. So locally, outside the nowhere dense set, that they are linear. Then we really would have this kind of strong non-linearity, or not field type implies linearity in the strongest possible sense. So this is this conjecture here. So let R be type B, let F be 0, 1, be continuous and definable. Is the picture I showed you on the previous slide that would always happen? Is F locally affine outside the nowhere dense? We do have partial answer in yes, yes for all known examples, but we really don't know in general. So I think this would be really nice. I want to maybe have a proof for this observation, but I really just want to, I'm not sure whether I give the proof. Really, if you stop following when I started talking about type B, type A, type C, dense omega orders, and so on, fair enough, but you can really ask this kind of question purely without any mentioning of all these things. So really what this now comes down to, and why I like this kind of question so much, is that so this is kind of the statement of the question, the first one, but this is equivalent to, in particular, the second statement here. So the question is, given a function f, 0, 1 continuous, the following statements are equivalent. Yeah, I really have to formulate this poorly. If type B is, if R is type B, then F is an affine outside the nowhere dense subset of 0, 1. This is equivalent to saying that if F is nowhere dense, nowhere locally affine, then it is of field type. So it's really so this kind of what the question I'm really asking here is that if you have a nowhere locally affine function over the real additive group, is that enough to define a field? I mean, this should be the kind of minimum question. What is the minimum linear behavior you could ask in general of a function? Is that it's nowhere locally affine? Is that enough to construct a field? And really, this is equivalent to that statement, because in the case type A and B, you already know how to handle this case. It's really just how can we recover a field from this kind of very non-affine functions? Yeah. So to go the last 2 slides, and I'm done. So really, the picture you should have in mind here. So if you want to let me summarize what we were doing for this nonlinear versus field type behavior, this is again the same kind of chart I showed before, but now with put some kind of properties in there. So here up here, so this is type A. This is what the generalization of homonomiality in the field type. Really, what we get, best thing we get for continuous function is that the Hrushovski-Steinhorn here, that they are almost everywhere differentiability. But if we add that we do not have field type, then we get that they're almost everywhere affine. So that you would have this kind of picture that we saw on the previous slide, this kind of distance to counter set kind of image. Type C, okay, type C was everything is defined, but doesn't matter for our question. And in type C, the best thing we currently get is if you have a C2 function, it has to be affine. So you really use this kind of trichotomy here between field type and no field type really gives you some kind of linearity, non-linearity, as one would hope. Yeah, one last slide coming back to this old result, which again has nothing to do with per se with any kind of monotheoretic tameness, is that remember we said that if you have a function from 0, 1 to r and it's C2 but non-affine, then you have field type. You can ask, of course, this question, okay, why C2? I mean, C2 because the function then have to be locally convex, more or less. But there's so what about C1? Can you do anything about C1? And we do have a result for that. It's a little bit harder to state. So we don't know in general whether this could be exchanged to C1. But what we do have is the following. Suppose you replace C2 by C1, and then you add somewhat the absolute minimal tameness condition you could possibly induce. Okay, you could probably even get lower, but is that you do not define an isomorphic copy of second order arithmetic. That's probably, I mean, I think we all agree that this is something that's not so bad. Then this works out. The problem is if you have C1, then the field could only be, could happen that it only lies on a nowhere dense set, not on a whole interval. Okay, so you don't have field type. But if you have a field on a nowhere dense set, then what you get is you can always define one of these or the older result of mine, which is isomorphic copies of, or on that thing, you can define on this nowhere dense set, you can define a model of the second order. So in particular, what you get, this is a slightly stronger statement in the type B case, is that if you have a C1 function definable in type B structure with a decidable theory, then it has to be. And this, all the examples we really know are for essentially it's more or less decidable theory. Okay, so you see this kind of general framework of non-linearity implying field type in the real field. We have some open questions, but in general, you see this. Many things are the whole outside the setting of the movement. So then let's say again, congratulations, Kobe, say again, and thank you.